morning, everyone. So last time we introduced the exponential map of a Lie group by using one parameter subgroups, and we also introduced quickly the Lie algebra structure of a Lie group. So let G be a Lie group. Then what we did was we equipped the tangent space at the identity element with a bracket structure, and for reasons that I will explain today, these two together are called the Lie algebra of the group G. Now, I think that most of you know the definition of a Lie algebra. A Lie algebra is a linear space equipped with a bilinear form that has two properties. First of all, it should be anti-symmetric, and secondly, it should satisfy the Jacobi identity. So my first goal today is to show that in that sense, this is indeed a Lie algebra. It satisfies these properties. Now, in order to prove this, I would like to go over, I really need the definition of these brackets, so I would like to quickly review the definition of the brackets. So starting point was, if you have an element X of the group, then we have a conjugation map from, I'm not completely consistent in writing, writing G. We consider the conjugation map, conjugation by X, from G to itself, and this map it's really an automorphism, and it's obviously smooth because the multiplication structure is smooth, so this was a Lie group homomorphism. And now we had a general statement that if we have a Lie group homomorphism, then there is a commutative diagram involving that homomorphism, its derivative, and the exponential maps. So there are the exponential maps, and there is the tangent map at the identity of Cx, which we denoted by add of x, and this is a commutative diagram. Now, this commutative diagram can also be expressed in terms of a formula, and I didn't have that formula on the blackboard last time. It's really a prominent formula. You should really know that formula by heart because it appears so often in the theory. Suppose that we have an element x in the tangent space, so actually, of course, it comes from this tangent space, which happens to be the same. Then what does the formula say? Well, it says, suppose that we first apply add of x to this x and then apply the exponential map. This is the same thing as first taking the exponential map and then applying conjugation on the level of the group. So the formula becomes, so let's first take this one, that the conjugation of x to x, x inverse, is given by the exp of add x, x. Now I said you should really know this formula by heart, but that's not very difficult if you adopt a certain point of view. The idea is that this is an element of the Lie group, and this is an element of the Lie algebra. And this formula connects a kind of conjugation on the group with conjugation on the algebra. And the connection is by getting this conjugation inside the exponential. And then it should really be this one. And this is basically the only choice one can make. So the only natural formula which does such a thing is this one. Now that helps, of course, this helps our memory. Now, there was a second diagram, and this diagram came out of the observation that the adjoint map introduced here really may be viewed as a Lie group homomorphism, and then it's called the adjoint representation. So there is the map, a joint map to the general linear group of the tangent space. Well, this is a Lie group homomorphism. If we have a Lie group homomorphism, then there is a commutative diagram involving the exponential maps of the Lie groups. So here we have this exponential map, and here we have the exponential map. So what is the tangent space at the identity element? That's the endomorphisms of the tangent space of G. And the exponential map is just a classical exponential of an endomorphism, which is given by a power series, if you like. And then, of course, here we should take the tangent map of the adjoint representation at the identity element, but we define this to be little ad. So this is a commutative diagram. And now we can do the same as we did above, and that is write in formula what it means to that this diagram is commutative. So suppose that we have an element x in the tangent space, then the statement is that if we first take the exponential map and then consider the image, and then consider add applied to the image, so then we consider how the exponential acts by conjugation on the Lie algebra. So the formula is take add of the exponential map, and then the formula, the commutativity of the diagram really asserts that the formula is that we may first take the add of x and then get a linear map here and then take the exponential. So this is E add of x. Now this is another very prominent formula that you really should know by heart. Again, it's very natural, so it's not difficult to remember. But you should have this available at all times. I mean, even at 2 o'clock in the night, even if you've had a party before. Good. Now, the brackets on the Lie algebra is defined by brackets of x and y is defined by we take add of x and we apply it to y. Add of x belongs to the endomorphisms of the tangent space, and if x and y are elements of the tangent space, this is the way we can define the bracket. Right? And then clearly this is bilinear, so the brackets is clearly bilinear. This is a map from here to here and is bilinear. Well, I should quickly recall, by the way, that this brackets, in the case that we start with a classical example, so suppose that our Lie group is the general linear group of a linear space, then the tangent space is the space of endomorphisms, and this bracket, in that particular example, is just a commutator bracket. And so this is the reason for using this bracket notation. For defining it in this way. The commutator bracket may be obtained in this way, and this is one of the reasons for using this notation. Okay, now secondly I want to show, so this is going to be a lemma. Secondly, I will show that this bracket is anti-symmetric, and this means that x comma y is minus y comma x. And then third important observation is that this bracket satisfies the Jacobi identity. Now there are several, because of the anti-symmetry of the brackets, there are several ways to write the Jacobi identity. I'm now going to put it in a form in which I will prove it. And that form basically says that the adjoint of x is a derivation with respect to brackets, so meaning that if I have y and z and take the bracket with x, so this is the same as add x applied to the bracket, then what I may do is first apply add x to y, take the bracket with z, so let's write it like this, x applied to y, and then bracket with z, and then add similar expression, but now with x bracketed with z. And this is this is perhaps not the form in which you may know the Jacobi identity, but if you use the bilinearity and the anti-symmetry, well, if you use the yeah, that's right. If you use the bilinearity and the anti-symmetry, then you can always get it in the form that you would prefer. But this is, in some sense, this is a very natural form, and I'm going to explain why. Okay, so our next goal is really to give a proof of this lemma. So let's first turn to the bilinearity. Well, that is really obvious from the definitions, because the adjoint map is a linear map, it's a derivative, so it's a linear map from the tangent space to the endomorphisms. So this explains the linearity in x. And now why is it linear in y? Well, because this map maps into the space of linear maps. So if I apply this to an element y, the behavior will be linear. So one is really from the definitions. Okay, 2. Well, first of all, it is a so the first step is to observe that if you have bilinear form, then its anti-symmetry is equivalent, so it suffices really to show that bracket of x with itself is 0. Why is that? Well, this is because of the bilinearity. Let's do that. Where I'll keep using one blackboard. Let's do it here. So So suppose that we have that. So this is really going to be a remark, a side remark. Suppose that we have that the bracket of two elements is always 0. Of course, this should be for all x. Suppose we have that. Then we can look at the bracket of x plus y with x plus y, and then use the bilinearity to express this as bracket of x with x, bracket of y with y, and then we have a number of cross terms, and this is x comma y plus y comma x. Now this holds for all x and y. Now suppose that we have that if we take the same element, so if we take any x, and suppose that we have bracket x is 0, that means that this expression is always 0. And this expression is also always 0. And this expression is also always 0. So we conclude that the sum of these expressions is 0. And this gives us the anti-symmetry. So it really suffices to show that. And so so I think it's a good idea to invoke the definitions for this. So what I want to show, I want to say something about add x applied to x. Now this one is defined as a derivative. I mean, you could also say it's defined as a derivative, so it can be written as the d dt at t is 0 of add of x tx x. Why is that? Well, apply the chain rule. The tangent, so for t is 0, this element is the identity element. The tangent map of add at the identity element is little add, and then you have to apply it to the derivative of this. The derivative of the exponential map at 0 is the identity map. And so we have little add, identity map, and then the derivative of this is x, at t is 0 is still x, so it's add x applied to x. So this is true. And the expression here can also be seen as the DDS. So let's write it with partial derivatives. At s is t is 0, take the x of s of add x tx on x. Right, so in fact I first want to, let me explain this formula. First want to differentiate with s. So what I'm really doing is for this expression I'm substituting that this is equal to a derivative with respect to s of this expression. So t is fixed, take the derivative with respect to s at s is 0. This is the first derivative that we take here. Then for s is 0, this is 0. Tangent map of the exponential at 0 is the identity. So we have the identity at the derivative of this. But the derivative of this expression is just add of x tx applied to x. And this is still so at s is 0. So indeed, by taking the derivative of this expression with respect to s and taking it at s is 0, we get the expression over here, but then there is another partial differentiation that remains to be done, and that partial differentiation is given here. So we have the identity of these two formulas. And now I'm going to use that, first of all, that the adjoint map is linear. So I can put the s here in front of the x. So maybe we should take a bracket here, and then the s may be put here. And then I'm using the formula that has been erased in order to make room for this formula. And that was that you may view the action of add really as a conjugation action on the level of the group. So this conjugation on the level of the algebra can be viewed at the outside of the exponential map as a conjugation by this element. So then we get this derivative at s is t is 0 of x tx x sx x tx inverse. But now we will use that exponential gives a one-parameter subgroup. And that means that we can write this expression as the exponential of tx, well really t plus s minus t times x is exponential of sx. And so that means that really the variable t doesn't appear in this expression anymore. And so that means that if we differentiate first with respect to t and then with respect to s, this may be done because we are in a situation of 2 times continuous differentiability, and then partial derivatives may be interchanged. So if we first differentiate with respect to t, this expression will give us 0, and then of course this will stay 0 if we differentiate with respect to s. So the answer is, the outcome of this is 0. Now if you look at the formulas, then you see that this really comes from the fact that the exponential gives us a one-parameter subgroup of the group. Okay, this gives us the anti-symmetry. So 2 has been established. We have now established 1 and we have established 2. So it remains to establish 3. Now, let me see, what is the... Right. So the proof of 3 is really based on a lemma, and that lemma will have another important application in a moment. The lemma says, so 3 will be derived ultimately from the following lemma. The lemma says that the bracket structure, and I think I told you last time already, that if you have a Lie group homomorphism, then it preserves the bracket structure, but we didn't give a proof yet. So suppose let phi be a homomorphism of Lie groups, then if we apply the tangent map of phi to the brackets of 2 elements, so these are the brackets coming from the Lie algebra of G, then we may also first apply phi to the elements x and y, and then apply the brackets of the Lie group H. So here this is true for all x and y in the tangent space of G at the identity element. And recall that the tangent map of phi at the identity element, phi maps the identity element to the identity element, phi goes from G to H, so this goes from the tangent space at the identity element to the tangent space of H at the identity element. Yeah, so this is another remark I want to make in order to be able to read this formula. So it means if I apply the tangent map of phi to x, then I get an element in the tangent space to H. And then I can take the H brackets. Now, I'll first prove this lemma, and then show that indeed condition 3, the Jacobi identity of the previous lemma, follows from it. And in order to prove the lemma, we have to go through all the definitions that are part of, well, we have to go through the whole definition process of little add, of the brackets. So first we have to study what happens with conjugation. So suppose that we have two elements, x and y, of the group. Then of course, because phi is a group homomorphism, we know that this holds. Now of course, we can now use...
The minus 1 should probably be over there, right?
Absolutely. The minus 1 should be over here. Thank you. This happens when I start thinking. Okay. So it's good to remind me that I should keep thinking. So this can be viewed. So this is a conjugation. So I may write this differently. It's really the composition of phi and the conjugation by x applied to y. And here this can be viewed as conjugation by phi of x. Of course, this is a conjugation in h now, and this is the conjugation in g. Never mind. And then composed with phi, and then applied to y. So first we apply phi to y, and then we conjugate by phi of x. Right? So this means we could also write this by a commutative diagram, if you like. And then we have, yeah, of course the question now is, so maybe I should put it like this. We have phi, we have conjugation by c of x, and now it's conjugation by phi of x, and the statement is really that this diagram commutes. Now the identity element here is mapped to the identity element here, the identity element here is mapped to the identity element here, and so on. And that means that we can differentiate everything at the identity element, and then by the chain rule, the commutativity of this diagram is preserved. Right? We could use the diagonal map to compare with. So this gives, by differentiation at the identity element, that the spaces that appear will be the tangent spaces at the identity element, and here we will have the derivatives of phi, and here we will have the derivatives of the conjugation at the identity element, but this was the adjoint representation of the group in the algebra. So this is add of x, the add from g, and this is the add from h of phi of x. And this diagram commutes for all x. For any x in the Lie group, we have this commutative diagram. And now the idea is to do a similar thing for little add. Let me see if we so how could we, so what we could now do is apply to a particular element of the tangent space here, and then so is this, I want to take a derivative of x. Now this can be applied to an element x, say, but let's do it for an element y, because this x I wish to differentiate at in the direction of capital X, and things should be applied to y and z. So what I could do is I could do this and then apply the tangent map. I'm not happy with this. This will definitely give a result, but I have in mind that when I prepared this, I did it a bit simpler. Right.
Can't we just start applying the definition of little ad? By viewing big ad as a map from the tangent space to the general linear space, and the same on the right hand side of the diagram.
It's always difficult to do this in front of the blackboard, but somehow I think I forgot to write down this step. Let's follow the suggestion. In particular, we can apply this same thing to phi being the adjoint representation. I think this was the suggestion. Who gave the suggestion? This is the suggestion, right? So let's do that. So apply.
My suggestion is to kind of.
No, this is not right, because I want to keep the phi. So let me follow what I have in mind. It will lead to a solution. Okay. So if we apply, but it is if we apply this element to here, then and we take the tangent map applied to this, then this is equal. I mean, this is about the only thing that we really can do, and I wanted to do this with y. So this follows from the commutativity of this diagram. Tangent map of phi applied to y. Okay? And now perhaps so now this expression, it depends linearly on y and on this tangent map, and therefore if I want to differentiate this, then differentiating this at the identity element will give me a linear map, and this is where the complications come in. So in order to simplify this, it is easier to use directional derivatives here, because then we can just apply a Leibniz type of formula. So let's do that. So what I'm now going to do is I'm going to plug in for x I'm going to plug in I'm going to plug in x of tx. This may be done because this formula holds for any x of the group. So I can substitute a one parameter subgroup, and then I'm going to differentiate with respect to t. That's the idea. Okay, and then I can also use the formula that this is equal to, this was one of our very nice formulas. If you like, I can write it like this: add of tx applied to y is equal to add h of e to the add of. So now I want to take the phi of the x. So this is the x from the group G of tx. I want to substitute the same formula. But now I have the commutativity of the diagram with the x's, exponential maps. So I can interchange the order of this phi and the exponential. Then here I have to use the exponential map of h, and instead of phi I have to use its infinitesimal version, which is the tangent map at the identity. So then this is equal to x of h applied to or composed with the tangent map of phi, and then this should be applied to t of x. Now this is linear, so the t can be moved here, and then this can be written as by using the formulas for the x. So maybe first I should write it like this: x of h, and then t times tangent map of phi applied to x, and then this should be applied to the tangent map of phi applied to y. And now this can be rewritten as e and then little add of h, and then of t times tangent map of phi applied to x, and then this applied to tangent map of phi applied to y. And now I can differentiate with respect to t, and then the observation is that because this is a linear map, the differentiation with respect to t can be done inside without changing, because this is linear. So if I now differentiate with respect to t, at t is 0, then the expression over there gives te of phi applied to the ddt. Maybe I should repeat the formula here. At t is 0, and then e to the add t of x, which is the same as t add of x, because add is linear, applied to y, equals, and then it's the ddt of e to at t is 0 at e to the t e phi of x. So now I've forgotten the joint map. So there should, so the adjoint of x t e phi applied to x, and this should be applied to y, to t e phi of y.
I think there's an x too many somewhere.
Is there?
Because all you want to do is take the t outside of x.
I think it's fine. I think it's fine.
Because way on the bottom right, there's no x on the in the exponential.
There is an exponential here. There is an x in the exponential here. This is e to the... Oh, I see what you're saying. Okay, thanks. Well, thank you. Okay, so what is the outcome? So this gives us that if we differentiate this, we get really add of x applied to y. So this is the t e phi applied to x comma y. And this is of course the expression we wanted. And now on the right hand side we have that if we differentiate this, then the derivative of this exponential is the same exponential times the add. Take it that t is 0, the exponential vanishes, and we get add of t e phi of x applied to t e phi of y. Whew. Which leads to the brackets, to these brackets. Now, when I look at my notes, I see that I just wrote corollary. Yeah, I was really too quick here. But fortunately, the process that one has to go through is very natural. And therefore I could reproduce it on the blackboard. Otherwise I wouldn't have been able to, I'm afraid. So this proves the lemma. And now recall, so the lemma, so what was the lemma? The lemma was that if we have a group homomorphism, then this gives that the derivative preserves brackets. So this is what I've written over there. That formula, that was the lemma. And now I'm going to apply the lemma to the adjoint representation. So what was my first goal with this lemma was to give a proof of the Jacobi identity. So let's now prove the Jacobi identity. So now I can use that the adjoint representation is really a group homomorphism from G to the general linear group of the tangent space at the identity. Right? And the lemma above says now that if I take add x, so if I take the tangent map at the identity of add and apply it to of that this preserves brackets. Oh! So I have been mixing up things and I'll get the Jacobi identity in another way. No?
Well, it'll work.
Will this work?
Yeah, actually just go, it will probably.
Because it's also natural, right? But then of course you have to follow the natural steps, and this is what I'm rethinking in my head. What about having a break now? Seems to be a good strategy. We'll continue in precisely 15 minutes.